Working with quantum computers can help us understand fundamental concepts in physics, computer science, chemistry, math, and more. But first, what is a quantum computer, and how does it differ from a classical computer? Today, I'll give you a primer on quantum computing so that you're ready to use it as a tool in your classroom. Depending on where you define its starting point, the field of quantum computing is now about 30 to 40 years old. And like any 30-something, it's beginning to mature. What was once almost entirely theoretical is now becoming relevant to real, open problems across many industries, from healthcare and material science to logistics and finance. Because of this shift, it's increasingly clear that today's university students may encounter quantum computers in their future careers, whether they're physics majors, computer scientists, chemists, or even economists. Quantum computing is no longer something reserved for specialists. It's becoming part of the broader scientific and technical toolkit. That's where this series comes in. In Qiskit in the Classroom, we show how quantum computing connects directly to core course material you're already learning. Using real quantum hardware available through the cloud, we'll explore foundational ideas while building practical skills that prepare you for the jobs and research problems of the future. So, whether you're a student, an educator, or just someone who wants to learn independently, this series is for you. In today's episode, I'll give you a primer on quantum computing so you'll have the tools you need to follow along with the rest of the videos and modules in the series. We'll begin with a brief review of key ideas from classical computing, then contrast them with the fundamental concepts in quantum computing. Finally, I'll show you how to put these ideas into action by running your very first quantum program with Qiskit on an IBM quantum computer. Before we can really appreciate what makes quantum computers different, it helps to ground ourselves in how classical computers work. You're probably already familiar with many of these ideas, so this will just be a quick refresher. Classical computers process classical information, and the fundamental unit of that information is called a bit. A single bit stores the answer to one yes or no question. It has two possible states, which we label 0 and 1. When we combine bits, each additional bit doubles the amount of information we can store. So, for example, with 3 bits, we can represent 8 states, say the numbers from 0 to 7. So the number 0 would be encoded in the bits like so, and 1 would be 0, 0, 1, 2, 0, 1, 0, all the way up to 7, which is 1, 1, 1. This is a base 2 or binary number system. Each position represents a power of 2, with the rightmost bit being the least significant bit, or the ones place, and the leftmost bit being the most significant bit, having a value of 2 to the m minus 1, which is 4 in this case. So, if you have m bits, they can be in exactly one of 2 to the m different possible states. Computers perform operations on bits by transforming their states with gates. We typically represent these gates as symbols on wires, where the wires represent the bits. Here are some example classical gates. The NOT gate flips a single bit from 0 to 1 or 1 to 0. The AND gate takes 2 input bits and produces 1 output bit. It outputs a 1 only if both inputs are 1. Otherwise, it outputs 0. So AND 1, 1 equals 1, and 0 otherwise. OR of 0, 0 equals 0 and equals 1 otherwise. Finally, we have the XOR gate, which stands for exclusive OR. XOR outputs a 1 if exactly one of the inputs is 1. If both bits are the same, both 0 or both 1, the output is 0. By wiring together gates, we can build circuits that perform more complex tasks. A classic example is the half adder here. It takes the input bits A and B and adds them together to get 2 output bits. An XOR gate computes the sum, labeled S, and an AND gate computes the carry, labeled C. The carry is named such because it does exactly that. It carries the 1 to the next binary position, just like carrying the 1 to the tens place in base 10 addition. So for each possible pair of input bits, the total value should satisfy A plus B equals S plus 2 times C. If you'd like, you can pause the video now and, using the definitions of XOR and AND gates, see if you can verify that it works. Okay, so classical computing is built from bits, gates, and circuits. Quantum computers share that same overall structure, but some of the details are very different. Here, I'll show how the classical computing basics are adapted to the quantum setting, and how this offers new ways to perform operations and solve problems. Let's start with the most basic building block, quantum bits, or qubits. Just as bits are the fundamental units of classical information, qubits are the fundamental units of quantum information. Like a classical bit, a qubit can be measured as either a 0 or a 1. In quantum mechanics, we usually write these states like this, where these brackets are called Dirac notation. And it's just there to denote that we're dealing with quantum states. But unlike a classical bit, a qubit doesn't have to be only 0 or only 1. A qubit can also exist in a superposition of both states. A general superposition of a single qubit looks like this. Psi equals C sub 0 times the state 0 plus C sub 1 times the state 1. A superposition state is sometimes described as being in both states at once. Analogies kind of fail here, but it's a bit more like being partly in one state and partly in the other. Here, C0 and C1 are called coefficients, and they tell us how much of the 0 state and how much of the 1 state are present in the superposition. These coefficients are generally complex numbers, so they can be written in the form C sub I equals the magnitude of C sub I times e to the I phi sub I, where this phi is called the phase. This is a crucial feature of qubits for which there is no classical analog. You'll see this phase show up again and again in videos throughout this series and throughout your quantum computing career. When we consider multi-qubit superposition states, you can really start to see how the power of superposition gets supercharged, literally exponentially. With classical bits, an m-bit system can be in exactly one of 2 to the m possible states. But with m qubits, the superposition principle allows us to have a state composed of all 2 to the m classically allowed states. So the state looks like this. Psi is the sum over I of C sub I times the state I, where I goes from 0 to 2 to the m minus 1. Here I is a so-called computational basis state, a state where each qubit is either 0 or 1. But this superposition only exists before the state is measured. Once you measure a superposition, it randomly collapses to a classically allowed state, which is one of these computational basis states. The probability of measuring each state is given by the square of the magnitude of the coefficients C sub I. So the probability P sub I equals the magnitude of C sub I squared. And because we're certain to measure something when we make a measurement, the sum of all of these probabilities must be 1. So the sum over all of I of the magnitude of C sub I squared equals 1. Finally, the last uniquely quantum feature that we'll discuss is entanglement. Entanglement occurs when the state of one qubit cannot be described independently of another. For example, consider this 2-qubit state. Psi equals 1 over root 2, 0, 0, plus 1, 1. Individually, each qubit has a 50-50 chance of being measured as 0 or 1. But once you measure one qubit, the state collapses to either one of these two terms. If you measure one qubit and find it in 0, the other must also be in 0. If you find a 1, the other is guaranteed to be 1. Entanglement can also produce opposite correlations, where measuring one qubit tells you the opposite value of the other. This correlation exists no matter how far apart the qubits are, which is why the act of measuring an entangled state is sometimes referred to as spooky action at a distance. Now we're ready to discuss quantum gates. Just as classical gates act on bits, quantum gates act on qubits. Some of these gates are analogous to classical gates, while others have no classical analog because they're manipulating the uniquely quantum features of the qubits. But even those that have a classical analog need to adapt to the new quantum setting. First, they need to act on superpositions. Second, in the circuit model of quantum computing, the number of qubits is constant throughout the circuit. This has implications for the gates that act on the qubits. The action of a quantum gate can always be reversed. Here's a far from exhaustive list of some key quantum gates. The X gate is the quantum analog of the classical NOT gate. This box here is its circuit representation. It flips the state 0 to 1 and vice versa, just like a NOT gate. If your qubit is in a superposition, the X gate will transform the state like so. X times C sub 0, 0 plus C sub 1, 1 equals C sub 0, 1 plus C sub 1, 0. The Hadamard gate, or H gate, is one of the most important gates in quantum computing. It creates superposition and has no classical analog. It looks like this. H times 0 equals 1 over root 2, 0 plus 1, and H times 1 equals 1 over root 2, 0 minus 1. And still other single qubit gates can change the phase of a qubit state. Because this phase is a quantum feature, these gates also don't have any classical counterpart. Now for the multi-qubit gates, the quantum analogs to the classical AND, OR, and XOR gates. One of the most important two-qubit gates is the C0, or controlled NOT gate. One qubit is the control, and the other is the target. If the control qubit is in 1, an X, or NOT gate, is applied to the target qubit. If the control qubit is in 0, then nothing happens. So if Q0 is in the state 1, then you apply an X to Q1. The C0 gate is essential for creating entanglement. While it doesn't have any direct classical analog, it can be used to construct the quantum versions of many of the classical gates. And in fact, any other multi-qubit gate that you can conceive of can be decomposed into a series of single qubit gates and C0 gates. So we could just stop here. But for the sake of this video, we'll introduce one more multi-qubit gate, the Toffoli gate, or controlled NOT. The Toffoli gate, or controlled NOT, uses 2 control qubits and 1 target qubit. An X is applied to the target only if both control qubits are in 1. If both Q0 and Q1 are in the state 1, then you apply an X to Q2. This can be seen as a quantum version of the AND gate, where the AND is applied between the 2 control qubits, and the value of that operation is stored in the target qubit. This third qubit is necessary for making that quantum AND gate reversible, as we discussed before. Now we're ready to apply all these concepts to write and execute your first Qiskit program. We're going to build a quantum version of the half-adder circuit. This is a nice way to bridge from classical to quantum by taking a known classical circuit and turning it quantum. But beyond that, quantum half-adders have real use in quantum circuits. It's often necessary to perform math on the qubits, and many complicated mathematical operations, from addition to multiplication to exponentiation, are all constructed from the basic building block of the half-adder. In Qiskit, we often organize our work using what's called the Qiskit patterns framework. This is a general workflow for approaching problems with quantum computers. It has 4 steps. First, mapping the problem to a quantum circuit. Second, optimizing that circuit for a specific piece of hardware. Third, executing the circuit on the hardware. And finally, post-processing the results. Now, for the simple circuit that we're going to build here, this might seem like overkill, but trust me, as you progress in your quantum computing career, you'll be grateful to have the workflow broken down like this. Let's start with mapping. Remember that in the classical half adder, we used an XOR gate to compute the sum bit and an AND gate to compute the carry bit. So we want to reproduce that same logic using quantum gates. To implement this on a quantum computer, we'll introduce 2 additional qubits, both initialized to 0, to store the sum bit and the carry bit. Here we create a quantum circuit with 4 qubits, the qubits A and B, and the sum and carry. All qubits, by default, are initialized to the state 0, so this circuit will add 0 plus 0. If we wanted to set A and or B to 1, we could just apply an X gate at the beginning to the corresponding qubit. Now we implement the quantum version of the XOR gate. We do this using 2 C0 gates, with both C0s targeting the sum qubit. The first C0 uses A as the control, and the second C0 uses B as the control. This means the sum qubit flips once if exactly one of A or B is 1, and flips twice, or not at all, if A and B are the same. This gives us the same behavior as the classical XOR gate. For the carry bit, we need something that behaves like an AND gate. That was the Toffoli gate that we discussed previously. We use A and B as the control qubits, and the carry qubit is the target qubit. If both A and B are 1, the carry qubit flips from 0 to 1. Otherwise, it stays 0. Finally, we measure all 4 qubits. This collapses any superpositions into classical bits so that we can read out the result. The measurement results will be stored in this classical register here. The circuit we just built is an idealized description. Real quantum hardware has constraints. Qubits aren't fully connected, gates have different error rates, and each processor supports a specific native gate set. To handle all of that, we proceed to step 2 of the pattern's workflow, optimization. Much of this step is automated with a Qiskit tool called the transpiler. We just need to choose the particular quantum computer, called the backend, that we're going to send our job to. That's done with this code cell here. Then we transpile the circuit. The transpiler assigns logical qubits to physical qubits, rewrites the circuit using the hardware's native gates, and applies techniques to reduce the impact of noise. All of these considerations will result in a transpiled circuit that looks quite a bit different from the original logical circuit. Here's our transpiled circuit. This is the set of instructions that will actually be sent to the quantum computer to execute. Now we're ready to run it. To do that, we use a sampler primitive. A sampler repeatedly runs the circuit and collects statistics on the measurement outcomes. Here we run the circuit 100 times, which we call shots. Each shot produces a single bit string result. Finally, our last step is post-processing. To visualize the results, we plot a histogram of the measurement outcomes. Each bar in this histogram corresponds to a measured bit string, and the height of the bar shows how often that result occurred. For the circuit we used, on an ideal noiseless quantum computer, we would expect to see a single bit string dominate completely. In practice, noise introduces some errors, so we may see a small spread of results around the correct answer. But as expected, the dominant bit string is 0, 0, 0, 0, meaning we confirm that indeed 0 plus 0 equals 0, of course. While this alone might not seem that useful, you'll see the wide variety of applications of quantum computing as you progress in the series. This video is, after all, just designed to get you started. After learning about qubits, quantum gates, and quantum circuits in this video, you should now have the foundation you need to use Qiskit in your classroom. If you'd like to go deeper into Qiskit and quantum computing and try running quantum circuits yourself, check out the module linked in the description below. And be sure to explore the rest of the videos and modules in the series. I'll see you next time.